Section 2.2 Set Operations. The operators in set theory are analogous to the corresponding operators in propositional calculus. For example, union of sets corresponds to disjunction operator. As always, there must be a universal set U. All sets are assumed to be subsets of U. Definition: let A and B be sets. The union of the set A and B, denoted A union B, is the set X in the universal set such that X belongs to A or X belongs to B. For example, if A is the set 1, 2, 3 and B is the set 3, 4, 5, the union of those two sets is the set 1, 2, 3, 4, 5. And here is the Venn diagram of the union. The inside of this ellipse A represents the set A. The inside of this ellipse B represents the set B. And the shaded region represents the union of A and B. The intersection of sets A and B, denoted A intersection B, is the set of all X in the universal set such that X belongs to A and X belongs to B. Note that if the intersection set is empty, then A and B are said to be disjoint. What is the intersection of these two sets? It consists of only one number, the number 3, because only 3 belongs to both sets. And what is the intersection of the set 1, 2, 3 and the set 4, 5, 6? The answer is the empty set, so these two sets are disjoint. The intersection is represented by the common part of the ellipse A and the ellipse B. The complement of the set A, denoted with A bar, is the set U minus A. A bar is all X in the union such that X doesn't belong to A. If U is the set of positive integers less than 100, what is the complement of the set X such that X is greater than 70? The solution is the set X such that X is less than or equal to 70. Of course, we assume here that X is a positive integer because the universal set is the set of positive integers less than 100. The Venn diagram of the complement. A is represented by inside of this ellipse. The complement of A is the outside of the ellipse. That is any point from the universal rectangle that is not in A. This is the blue part of U. The difference of A and B, denoted A minus B, is the set containing the elements of A that are not in B. So A minus B consists of all X such that X is in A and X is not in B, which is exactly the intersection of A with the complement of B. The Venn diagram of the difference of A and B is represented by this blue region. It is contained, of course, in A and in the outside of B. The cardinality of the union of two sets. This is known as inclusion-exclusion principle. The cardinality of the union of A and B is equal to the cardinality of A plus the cardinality of B minus the cardinality of the intersection of A and B. For example, if A is the set of all math majors in your class, and B is the set of all computer science majors, the union of A and B is the set of all students who are math major or computer science major. So we can count the number of math majors, the number of computer science majors, add those two, and subtract the number of students that have joined computer science math major. So to count the union of two, the cardinality of the union, we count the number of elements in A, the number of elements in B, and then add them and subtract the number of elements in the cardinality of the intersection of A and B. Here are some review questions. U, the universal set, consists of the numbers from 0 to 10 integers. A is 1, 2, 3, 4, 5. B is 4, 5, 6, 7, 8. What is the union of A and B? The numbers from 1 to 8. The intersection. These are the numbers that belong to both A and B. And these are 4 and 5 only. The complement of A, any number that is in the universal set, but not in A. So this is A bar. What is B bar? The complement of B. Any number that is in U but not in B. So from 0 to 3 and then 9 and 10. A minus B. And now all numbers that are in A but not in B. And these are the numbers 1, 2, and 3. B minus A. All the numbers in B that are not in A. And these are only 7, 8, and 6. So 6, 7, 8. The symmetric difference of A and B is denoted with this A, O plus B, and is the set A minus B union with B minus A. This is the Venn diagram. So, an element that is in A but not in B, and an element that is in B but not in A. The shaded region represents the symmetric difference. And here, if A is this set, B is this set, then A plus B is what is the intersection here, 4 and 5. So everything else from the union is in the symmetric difference. So 1, 2, 3, 6, 7, 8. These set identities are obvious: identity laws, domination laws. Here U is the universal set, and you know that A is always a subset of U. So the union of A and U is U. The intersection of A and the empty set is the empty set. Idempotent laws: A union with A is A, the intersection with A is A. Complementation law: the complement of A and then its complement is just A. These set identities have names: commutative laws, associative laws, distributive laws. All these identities must be proved, and we see how we can prove some of them. The next identities for sets are De Morgan laws. The complement of union of A and B is the intersection of the complement of A and the complement of B. Here, complement of intersection is union of complements. Absorption laws: A union with A intersection with B is just A, so B disappears. A intersection with A union with B is A, again B disappears. Complement laws: the union of A and its complement is the universal set. In the intersection of A and its complement is the empty set. To each of these set identities, we have a corresponding identity of propositional logic. We'll consider three ways of proving set identities. In the first way of proving, we consider a given set identity. There is a set on the left side and on the right side of the equality sign. So we have two sets, and we have to prove that each of these two sets is a subset of the other set. The second way of proving is a set identity is to use the set builder notation in propositional logic. And the third way is to use membership tables. We'll see what is that in a moment. In this example, we prove this De Morgan law, and we'll use the first approach. We'll prove that the set on the left side is a subset of the set of the right side in 1, and then in 2 we'll prove that the other set, the second set, is a subset of the first set. To prove this inclusion, we start with selecting arbitrary element of the complement of A intersection of A and B. So X belongs here, and our goal is to show that X is an element of the second set. This means that X does not belong to the intersection of A and B by the definition of complement. This means that the negation of this is true. The negation of X belongs to A and X belongs to B, because the intersection of A and B is defined this way. Now we can use the De Morgan law for propositional logic. Negation of conjunction of two propositions is equivalent to disjunction of negated propositions. But what is the negation of x? X belongs to A. It is x doesn't belong to A, and this is x doesn't belong to B. This means that x is an element of the complement of A, and this means that x is an element of the complement of B. And we have OR here, which means that x belongs to the union. So we prove that any element of this set is an element of this set. So we have this inclusion. Now we have to prove that the second set is a subset of the first set. We start with selecting any x in the union of A bar and B bar, and we have to prove that this x belongs to the other set, which is the complement of the intersection of A and B. And this is done similarly to what we did in the previous slide. So I leave this for you to follow. Having proved both inclusions, we conclude that we have equality. Now we'll prove the same equality, the De Morgan law, using the set builder notation and propositional logic. The complement of the intersection of A and B is any x such that x doesn't belong to the intersection, which means x such that the negation of x belongs to the intersection of A and B holds. And here, when x is the intersection, when x belongs to A and x belongs to B. So we can replace this with the negation of x belongs to A and x belongs to B. We have equal sets. Then negation of conjunction by the first De Morgan law is equivalent to disjunction of negated propositions. So we have equality here. Then this means that x is not in A, and this means that x is not in B. X is not in A means that x is in A bar, and this means that x is in B bar. And we have disjunction here. Disjunction corresponds to union. So this means that x is an element of A bar union with B bar. And this set is just the union of A bar and B bar. So we prove that the complement of intersection of A and B is equal to union of complement of A, complement of B. Now we'll illustrate the third method of proving set identities by proving this distributive law using a membership table. First, we have three sets, so we start drawing a table and write a column for A, column for B, and column for C. Then we consider different types of elements of the universal set. If an element of the universal set belongs to A, we write 1 in that row. In the first row, we select an element in the universal set that belongs to A, B, and C. In the second row, we select an element of the universal set that belongs to A, B, but that element doesn't belong to C. And we have to write all possible combinations of belongings. For 3 sets, we have 2 cubed, 8 possible combinations. This is similar to what we did for truth tables, for propositions. If we have 3 propositions, the table will have 8 rows. And here similarly, 3 sets, the table must have 8 rows, and we write all possible combinations of belongings to the sets. 4 ones for A, 4 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros for B, and then 1 0, 1 0, 1 0, 1 0 for C. This way we are done with the first 3 columns. Then we look here, and in the left hand side we have, in this parenthesis, intersection of B and C. We start a third column, label it with B intersection with C, and then fill this out. In the first row, the element belongs to A, belongs to B, and belongs to C. Because this element belongs to B and C, it will belong to the intersection. In the second row, the element belongs to B but doesn't belong to C, so it doesn't belong to the intersection of B and C, so I write 0 here. And we continue like that to fill out the column for intersection of B and C. Then we can write a column for the left hand side. It is the union of A and B intersection C. What shall we write here in the first row, in this column? In A we have 1 here, the intersection of B and C 1. So in this row, the element in consideration belongs to both sets here, so it belongs to the union. In the second row, the element belongs to A, doesn't belong to B, doesn't belong to B, so it belongs to the union. In the third row, the same thing. The element belongs to A, doesn't belong to the intersection of B and C, but it belongs to the union of these 2 sets. In the last row, in the last row, the element doesn't belong to A, doesn't belong to the intersection of B and C, so it doesn't belong to the union. This way we fill out the whole column for the left hand side. Then we write a column for the expression in this parenthesis, A union and B. Fill this out, it will be empty in the beginning. How we fill out? We look for values of A and B in their columns. In the first row, we have 2 ones here, which means that the element under consideration belongs to A and B, so it will belong to the union of A and B. We write 1. And we continue like that. Then we start a column and label it with A union C. It will be empty in the beginning, then we fill it out with looking for values in the column of A and in the column of C. In the first row both are 1s, both values, which means that the element under consideration is in A and it is in C, so it will be in the union of A and C. We write 1. In this row, the element under consideration is not in A, not in C, so it will be not in the union of A and C, so I write 0 here. So working that way, fill out this column, and finally we draw a column for the expression of the right hand side, which is the intersection of the last two sets. In this row we have an element that belongs to this set and to this set, so it will be in the intersection of those two sets. We write 1 here. In this row we have an element that is in the first set but not in the second set, so that element will not be in the intersection of these two sets. We write 0. This way fill out the whole column, row by row. And finally, we compare the columns of the left-hand side of the equality, that is this column, and the column of the right-hand side of the equality, that is this column. They coincide. We have 5 ones, 3 zeros, and here we have 5 ones, 3 zeros, which means that every element in the universal set belongs to the left-hand side if and only if it belongs to the right-hand side. So those two sets are equal. Let A1, A2, and so on An be an index collection of sets. Here N is some positive integer. Because of the associative law for union and the associative law for intersection, we can define union of n sets this way and intersection of n sets this way. For example, if AI is defined like the set of all integers greater than or equal to I, then the union of these sets, AI for I from 1 to n, is just the set 1, 2, 3, and so on, that is the set Z plus. And the intersection of these sets AI for I from 1 to n is just An.